Here we see a source connected in series with a capacitor. Same situation we've been looking at. Small resistance here, or maybe a larger resistance. It doesn't really matter how big the resistance is. We'll call that the resistance of the source, but we could throw a resistance in here and effectively add that to the resistance of the source. Whatever resistance is in the circuit, total resistance around here, we'll call RS. When we hook the generator up to the capacitor in that specific instance, this is just the resistance of the source. The voltage across the capacitor is Q over C. The current flowing through the circuit is just the total voltage divided by the resistance. Now, there's a voltage across the capacitor that fights the voltage of the source, so that the net voltage is voltage of the source minus the voltage of the capacitor. We divide that by the resistance of the capacitor, and we get the current. Now, what's the current? As we've seen, current is the rate at which electrons are pulled off of this capacitor plate and pushed onto this one. So that the current is the rate at which the charge in the capacitor changes. Okay, the number of coulombs per second by which the charge in the capacitor is being changed. Now, setting dq over dt equal to Vs minus Vc over Rs, if we let Vc equal Q over C, we plug that in for for Vc, and set this equation down. This becomes a differential equation. dq over dt is Vs minus Q over C, all divided by Rs. And we can solve that differential equation rather easily. It's a separable differential equation. Now, for non-university physics students, you don't have to worry about the details of that solution, obviously. University physics students should understand those details. What happens, and university physics students will verify this, is that the charge on the capacitor then has this functional form, C Vs times 1 minus e to the negative t over Rc. This is an exponential approach to the charge C times Vs. That is, when t becomes very large, e to the negative t over Rc will approach 0, so that this factor will just be 1. So that Q will be C times Vs. And that's exactly what we expect. We expect that the capacitor will keep building charge until the voltage across the capacitor is equal to the voltage of the source, equal and opposite. When this thing has a charge that's equal and opposite to the source voltage, all current flow will cease. Now, if the voltage across the capacitor is equal to the source voltage, what's the voltage across the capacitor? It's just Q over C, so Vs should equal Q divided by C, which is exactly what this equation says if t is large. At least we approach that state if t is large. At t equals 0, of course, we have 1 minus e to the 0, and we're implicitly assuming here, I guess, that the capacitor is initially uncharged, because e to the 0 is 1, 1 minus 1 is 0, so Q would be 0.